Okay, so it should be going. So here's our recording. Welcome. I'll go ahead and open up the PowerPoint. So this is the end of chapter 15. What I'd like to emphasize is there are some parts of chapter 15 that aren't the focus of what you're required to know come quiz and exam time. So what you see in this lecture is what is emphasized for things like quizzes and exams. And I'd like to refer us back to the content pages where you find the lecture notes. There is a section called Learning Outcomes, a bullet point list. Treat that as your study guide when it comes to what to know about this particular part of the chapter, as well as the previous parts and the parts to come. So when it comes to, do I need to know about a certain topic, I try my best to be as detailed as possible with those bullet points for things that you need to know. Whenever you're in doubt about that, you can always come to me and ask me, is this section or is this part going to be on covered on a quiz or an exam or homework? And I'll be happy to let you know. So as we go through, this is what I'd like you to know about. And if you need further reiteration, the content page where you find the notes has the bullet point list of what to know. And then again, when in doubt, come to me for that. Okay, so I'll be happy to answer those questions as we go along. So with that, the chat is open. So if you'd like to send questions my way when there's sort of that pause for answering questions, I encourage you to participate. You don't have to speak if you don't want to. You can type if you'd like. But I love the participation. Try to make it as interactive as possible, even though that it's not in person, it's virtual. So please be aware that those are ways that you can contribute or get my attention as we go. The chat is open. So we are finishing up the chapter talking about turning kinetics data, the data about the speeds of reactions, into a bigger conceptual picture. In fact, how molecules are involved in chemical reactions just by knowing the speed information of the reaction. And so, let me click, there we go. What we're doing is, and what our path has been for this chapter has been to take experimental data and, oops, now I'm having technical difficulties. Okay, there we go. Experimental data, and we use that data to determine rate laws, equations that tell us how the speed of a reaction, right, the reaction rate, is related to concentration. And concentration can have varying effects on the speed. We've seen first order, where it's a direct relationship. We've seen zero order, where there is no relationship. You can have whatever concentration you want, and it won't affect the speed. And last time we talked about integrated rate laws, those equations, which, yes, we need to memorize, those integrated rate laws that answer different questions, specifically the relationship between concentration and time. So how long will it take to reach a concentration? All of this hard work, all of these last few lectures are together going to combine to give us a bigger picture of what's going on chemically, a window into the molecular world. So the question is, how does that happen? So what kind of information, where are we focusing our attention on when it comes to answering these questions? So taking the generic form of a rate law, rate equals the rate constant times the concentration of reactant to its order, we find that the reactant orders play a part in determining what the reaction mechanism is. And I like to think of this as the molecular play-by-play. A mechanism is basically the explanation on the particle level what's going on. When I mix these reactants together in a solution, then what are the particles literally doing to make the products? That's going to actually come from the order of the reaction that we get from experiments. The other thing is that rate constant. I mentioned it was important, but all this time we've just been saying it's a number with units that's necessary for the math. Now we're at a point where we can say the rate constant actually has more involved more involvement in the picture of what's going on. In fact, the rate constant itself, this one number, actually secretly hides the effects of temperature, energetics, and how orientation is a part of chemical reactions. So not just that reactants bump together in a beaker, but they bump together in the right way, in the right orientation. To have this conversation, this might be the number one most important slide to make everything else in this lecture make sense. The key to our descriptions is relying on collision theory of chemical reactions. And it's pretty straightforward when you think about it. Collision theory means that reactants need to collide with each other for a reaction to occur. If A and B make C, then at some point, A and B have to communicate with each other, and they communicate with each other through collisions, through bumping into each other. So the first thing is reactants need to collide for a reaction to occur. The rate of collisions directly relates to the reaction rate. So that's our R. So whatever factors impact collisions will impact how fast a reaction happens. So that's factors that affect collisions will affect the reaction rate. So that's the bottom line. To understand what's going on, we have to have this theory. We have to say molecules have to bump into each other, and what affects their bumping into each other affects how fast a reaction goes. So that can be our connection between experiment and the microscopic world. So let's go ahead and start the conversation by introducing a really important graph that you will see not just in this lecture, but a few more places in the course. This is a reaction coordinate energy diagram. So what this means, there is a graph with an x-axis called reaction coordinate. And reaction coordinate is not a measured, a measurement type axis. It doesn't have numerical values, but it's a reference of progress. So at the very leftmost point of the x-axis is the start of a reaction. This is where our reactants are sort of floating around in the beaker, and the very right-hand portion is the products of the reaction. So that's the reaction coordinate. It just is how far along, and the middle is the middle of the reaction. The y-axis is energy, and we see a few things. We're going to use this general reaction as our guide and our example for dissecting what's going on the small scale with kinetics. So this reaction is going to be a hydrogen molecule and a fluorine atom will bump into each other and make a hydrogen fluoride molecule and a hydrogen atom. And so by the collision model, we're saying an H2 molecule has to bump into a fluorine atom, and when they bump into each other, they will make the products. So that's what's going on here. So our reactants, this line, is telling us the energy starting point for our reactants. So this horizontal line on the left-hand side is going to be, this is how much energy H2 and an F atom have at the start, based off of their bond energies and so forth, and their kinetic energy. The right-hand side, this horizontal line is the energy of the products. So this is how much energy, based off of the calculations of bonds and so forth, is the HF and the H atom. Similar to what you've seen in first semester, the difference between the energy of the reactants and the products is a special quantity that we still need to know about. That difference, that subtraction, products minus reactants, is our reaction enthalpy change. So that's still going to be an important part that we're going to utilize, and we're going to have an entire module on thermodynamics later on. So we have that as an important feature to recognize for a reaction coordinate diagram. But okay, left-hand side, right-hand side, what is going on in this middle? This middle point is not straight lines, it's curves. In fact, we'll see it can be several bumpy curves, but what's going on in the middle of the graph? So that middle of the graph will always have at least one bump feature. This curve that we have is called, or designates, I should say, the activation energy. And activation, like it suggests, is starting, right? Activate, start. So it's symbolized EA. It is the energy necessary, usually in kilojoules per mole, needed for reactants to reach the transition state or the highest energy state of the reaction. So we think about it in terms of collisions. If I have an H2 molecule and an F atom, and they're trying to make their products, there must be some point in the middle where the two H atoms start to separate from each other, and one of the H atoms starts bonding to the F atom, and that's how the product is going to be made. But there's going to be this point in the middle where that central H atom is halfway bonded to its partner H atom and halfway bonded to the new F atom. And if we remember our rules of Lewis structures, this is not a good Lewis structure to have a central H atom. So this is unstable. Molecules do not like to do that. But that is an important part of how this reaction happens. This has to happen for the reaction to occur. So what it tells us is that reactions have to go to an unfavorable middle point called a transition state, a state where they're reaching that point of no return, that middle point where they're about to convert from reactants to products. And this is an unfavorable in terms of Lewis structure rules, in terms of energy rules. It's unfavorable. So that's why there's a big bump in energy on this graph. The reactants have to pay a price in order to become products. They have to reach this point. So we call this bump the activation energy. It is the vertical, it's measured by the vertical distance between reactants and the topmost point. And that tippy top peak is the transition state. That is where the reactants bonds are breaking and reforming. And if we want to draw it out as a Lewis structure, we usually, like we see here on this side, we bracket this bad Lewis structure and we put this symbol that you see here. This is called a double dagger. And that means this is our transition state. This is the unstable middle point a reaction has to go through to reach products. So the first thing about collision theory is we have to collide and we have to pay a price to become products, our activation energy. Now, thinking about it as this price we have to pay, and it's a vertical distance going up, we can start to think about what should be the relationship between increasing activation energy and the reaction rate. If I have a reaction with a small activation energy, a small price to pay, versus a large price to pay, we can start by asking the question, do you think that having a larger activation energy, having a really tall hill to go over, having a tall activation energy, will that make it easier or harder for the reactants to become products, having a large activation energy? And I'm happy to see an answer if there's anybody who wants to answer in the chat or out loud. If I have a large activation energy, is it easier or harder for my reactants to travel over to become products on this graph? Yep, exactly. It should be harder, right? Just like physically, if a person were to climb a hill, a taller hill will be more effort. So we would expect that a bigger activation energy means the reaction has a harder time getting from reactants to products. Now let's take it to speed. If a reaction has a harder time going to products, does that mean it should be going faster or slower, right? Harder time getting to products. Does that mean it should be faster or slower?
Slower.
Yep, exactly. Yeah, good job. Slower. So as activation increases, we should expect that the rate goes down. Reactions with large activation energies, a higher price to pay, will go slower than reactions with lower activation energies. So that's the first thing that we can gain from looking at a reaction coordinate diagram. That if the graph has a large activation energy, the reaction should go slower. And of course, if there are any questions that come up about slides, please feel free to ask or type in the chat, and I'd be happy to clarify. So that's the first effect or the first factor that influences what we've been seeing about speeds of reactions. Why does a reaction go slower? Well, one factor is if it has a large activation energy. The other factor is temperature. So to use this uh, idea of physical movement, we can talk about hikers traveling over a hill. And just to go back to activation energy, it is a correct statement to say that they're going to have somewhat of an inverse relationship. We'll see that relationship specifically in the equation. But yeah, as activation goes up, the speed will go down. And so that's activation energy. When it comes to moving over the hill, we can use the idea of hikers trying to get to get to the ocean or something. There's a sand dune, a hill in the way. So we can think about, in general, molecules bump around kind of like hikers that are trying to just run up a hill. If they happen to, have a large group, there's going to be a distribution of how much effort or energy the hikers can use to travel up the hill. Perhaps some people don't have enough energy, enough steam to get up the hill, and they might fall back, not fall. They might not make it down, up, and over the hill, and they might go back down that hill. So that's going to mean that not every person is going to make it. But in this analogy, what if we give people the energy they need? What if we give them an energy drink or a nice piece of fruit or some snack that can help them? Well, if on average, everybody has more pep to them, more energy for them to go over, well, then statistically, it's more likely that they can pay that price that could go up that hill and make it over to products. So there's an idea that if we give our hikers more energy, it is more likely that they will cross over. And the same thing will happen to particles. If particles on average have more energy, then they are more likely to go over the hill. We will see more people traveling over per second or per minute. And when we're talking about giving particles energy, we're talking about temperature. So what we're saying is if we give particles on average more energy with temperature, they are more likely to get over that bump and become products. So now we have another factor that influences how fast a reaction can go forward. We have temperature. So based off of this analogy, what should be the effect? As temperature goes up, is the reaction going to get easier or harder to become products? Hopefully we see it's easier. So then if giving higher temperature, more energy to particles makes it easier to go to products, do we expect temperature to make the reaction go faster? Higher temperature, faster reactions? Temperature goes up. Yeah, the rate goes up. So our next factor, as temperature goes up, the rate goes up. So there are some key takeaways that we get about how we can interpret reactions being slow and reactions being fast. So there might be some discussion about activation energy, and there might be some discussion about temperature that's involved with why reactions go slowly or quickly. Oh, sorry. Sometimes it's confusing how to click on this. Okay, there we go. So to jump into the math part, all of that information that we're collecting about the factors of why things go quickly and or slowly is wrapped up in the equation you see here called the Arrhenius equation. So the Arrhenius equation is an equation that wraps up all of the factors about what's going on with the molecules and relates them to the rate constant. So that's why K is such an important number when we were exploring it. And I said, hold on to that. So K is directly affected. The size of K is directly affected to some of these factors you see right here. And since K is a part of the calculation of speed in the rate law, R equals K times concentrations to their orders. If K is varying, then speed varies. So if a reaction has a high K, a large K, we expect it to be, on average, a faster kind of reaction. So K is a surrogate for telling us whether something is fast or slow, since K directly goes into the calculation for how fast or slow something is. We see a few things. We see activation energy is in this equation. So A equals A times E to the minus EA. So there's our activation energy. And we see our Kelvin temperature, and emphasis on, for these calculations, it has to be Kelvin. Has to be Kelvin. So reminder, Kelvin equals Celsius plus 273.15. Does it make sense what we've talked about based off of this discussion for activation energy and temperature? The first thing we said was that if activation energy is larger, then the reaction should be slower. So what would happen if I put a larger number in the top of a negative fraction that happens to be the exponent of E? So what happens when the number inside this parentheses gets more negative? We can test it on a calculator. So let's put bigger negative numbers in here. So if EA gets bigger, and let's for now forget that everything else is present. Well, let's do E to the minus 1, E to the minus 2, E to the minus 3. So what we see is if we make activation energy larger, then the math comes out to, so hopefully you have a calculator by you can prove it to yourself. If we make the activation energy larger, my calculator is saying that my answer is getting smaller, which is my rate constant. So as my activation energy gets larger, the barrier I have to cross, K, the answer, is getting smaller, and smaller rate constants lead to smaller speeds. So yeah, that works. Now, what do you think? Does having T in the bottom of this fraction result in what we've concluded about temperature? We can do the same thing. Try to put E to the minus 1 over, and in 1 over 1, E to the minus 1 over 2. So make the bottom of the fraction bigger. You'll see the opposite effect. You'll see that the answer gets bigger. So as temperature increases, the rate constant increases, and that's going to suggest faster rates. So first, yes, this equation does make sense with logically what should happen with collision theory. Other things about this equation, we have R. R is the ideal gas constant, however, and this is going to be true throughout this entire course. There's only one tiny place where we use it with other units. But in this course, R is going to be converted to units of energy always. So the ideal gas constant is going to be equal to 8.314 joules per mole Kelvin. So that's going to be an important number to memorize. When we use the gas constant in this course, we are going to use the energy units of the gas constant, 8.314 joules per mole Kelvin. One thing that's interesting that I came up with to help memorize it, how I memorized it, is you will notice that the digits after the decimal point, 314, are the first three digits of pi, right? Pi is 3.14, blah, 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 blah. So one way I remember it is if the gas constant needs some energy, or how did I, well, whatever. If the gas constant needs some energy, it ate pi. It ate pi. Hope you like that. So that's how I remember it. The gas constant in units of energy, R is equal to 8.314 joules per mole Kelvin. And that's because the units need to be able to cancel inside the parentheses for this equation's dimensional analysis to work out. And that only happens if R has these units. There is one more part to the Arrhenius equation, and that's called A. A is the frequency factor. And the frequency factor, it has a lot wrapped into it, but for us, we're just going to focus the frequency factor. Basically, like its name suggests, it's about how often. And basically, it's a number that wraps up how often the reactants have a successful collision. And so what that means is if colliding also requires you to collide at a certain angle or a certain geometry or orientation, well, that's going to affect how fast the reaction goes, because that means not every collision will be at that correct angle, and that's going to have an impact. So simpler collisions will mean a faster rate. And just to demonstrate how this orientation matters, we can take our previous example, a hydrogen molecule and a fluorine atom. Well, if they bump into each other like this, then they match the transition state where a hydrogen is sort of being sent off to bond with the fluorine atom. But if the two molecules bump at a 90-degree angle, then they don't have that geometry where one of the hydrogen atoms gets attracted to the fluorine atom. So there's an orientation that is necessary to make the reaction go forward. That conversation, that issue, results in the size of this number, which we call the frequency factor, how often the collisions are successful based off of how simple or how complicated they have to collide with each other. And you can see, we can do the same analysis. If A gets bigger, then what happens to our answer? A is outside of the exponent, so it's just a coefficient. So if a coefficient gets bigger and the rest of it stays the same, is the number answer for K going to be bigger? Yeah. If it's 2, 3, 4, then it's going to multiply it by those factors. So what we see is that if we have a simple collision, we should expect easier times and larger frequency factors. And so that's the hidden secret of K, and how having knowledge of this number gives us an inside view of what's going on in the reaction. I did an experiment and I found out my K was really small, but this reaction's K was really big. What does that mean? Well, it means there's something going on inside the reaction. So K, the rate constant K, represents all of the molecular considerations that influence a reaction wrapped into a single number. K depends on temperature, the size of the activation energies, or their barriers, I should say, the rate of collisions between reactants and products, and the orientation they need. So when we did those rate laws, we had this K and we kind of took it for granted. It was just this number, but now we know K is actually secretly, based off of the Arrhenius equation, something that wraps up every important detail about how molecules have to bump into each other, collide, and we call that collision theory, but how they get together to make their products. And so that's our conversation about rate constant and how it impacts our knowledge of reactions. I will pause here if there are any quick questions about what we did. Awesome. And again, you can always private or direct message me, I guess, as well. Okay, the second way kinetics helps us view what's going on inside reactions is through reaction mechanisms. So what is a reaction mechanism? It is a series of elementary steps, so new vocabulary, involved in an overall reaction. So a couple things, an elementary steps means basically the sequence of events. And in this case, we're talking about the sequence of collisions. So another way to think of it is like a play-by-play. Step one, the reactants have to bump in like this. Step two, now that they're bumped in like that, they then have to bump in like this, and so forth. So those are called elementary steps. They are literally what the molecules have to do via collisions to become products. And overall reaction is what we experience. It's the balanced chemical equation. A couple things about how we interpret mechanisms and how we analyze mechanisms, like what's going on. If a mechanism is valid, if it makes sense for the reaction, there are a couple things. The steps must sum to the overall balanced chemical equation, and this works the same way as first semester. It's Hess's law. If you combine reactions, remember crossing out things as they come, if it comes out to the overall balanced reaction, then it checks step one of being a good mechanism. The next part is a little bit new. The rate law of the rate determining step of the mechanism must match the experimental rate law. So what do we mean about rate determining step? Well, first of all, like its name suggests, it controls the rate. It controls how fast we go. For this reason, the rule that we have is the slowest part of the reaction is the rate determining step. Like you see here in this drawing I made of two funnels. Well, if we're thinking about how water getting from the top to in at the bottom of this beaker, it has to go through two steps. It has to go through funnel number one, and then it has to go through funnel number two. Well, if funnel number one is really huge, it's very quick for the water to just pour right through. But going through funnel number two, since it has such a tiny opening, there's going to be a bit of a clog when it comes to being able to pass through. It's going to slow down the drip of the water making it to the end. So we would say this second funnel step is our rate determining step. Our slowest step is our rate determining step. And so the rule is when it comes to describing reactions, the slowest step must match the experiment's rate law. And so we'll see how that works in the next slide. Okay, so these are the two criteria that impact whether or not we have a good mechanism. In some cases, the balanced chemical equation is also the mechanism. So let's take our example from earlier. We have a hydrogen molecule and a fluorine atom, and we could say that this reaction literally is depicting the collisions that have to happen to make the products. An H2 molecule must bump into a fluorine atom, and that's how you get them to make products. So I have a little picture here showing that. So a H2 molecule and a fluorine atom bump together, and then they'll make their products. In the case that the reaction is its own mechanism, then that is called a one-step mechanism, right? There's only one description of what's happening. The reactants, just boom, make the products. So we call that a one-step mechanism. So in that case, what would be the rate law based off of that information? So this reaction is controlled in one step. The speed depends on the collisions involved in that step, which we call the molecularity, and the rate law is based off of the molecularity of the step. Molecularity meaning how many molecules are involved in the collision in that step. So specifically, when we talk about molecularity, we are talking about what has to collide. We are focused only on the reactants of that step. Those are the things that need to collide, okay? So what needs to collide? Hydrogen and fluorine. So that means our rate law will be the rate is equal to the factors about that influence that step wrapped into that nice number called the rate constant, K, for that step. Since I labeled this step 1, I'm calling it K1, just to, it'll be more useful in more complicated mechanisms, but that's how we do it. This is the K for this step, so K1, times the molecules involved in the collision for that step. So it depends on how much hydrogen is there. So that's why we'll put times the concentration of H2. And it depends on how much fluorine is there. So that's why we'll put times the concentration of fluorine. So every time we're looking at the mechanism of a step, it works this way. An elementary rate law comes directly from the reactants in that step. For this particular step, this would be the rate law. So how do we know if this is valid? Through experiments, making sure that it matches. So this is an actual paper that I found that looked into the kinetics of this specific reaction, hydrogen plus fluorine atoms reaction. And this was our result of what the rate law should be for that mechanism. R is equal to K1 times H2 times F. So our answer from the previous slide is that we predict from the mechanism, the explanation, that this is my rate law. If this is my rate law, the first question I'll ask you guys is, we talked about rate laws a lot in lecture 2, okay? What is the overall order of this rate law? What is the overall order of this rate law?
2.
Mm-hmm. It is 2. So this rate law has an overall order of 2. So it is a second order reaction. And therefore, the rate constant should have units related to a second order description. Like we mentioned, we talked about the units. So let's actually see if that comes out. So in this paper, they actually calculated the units, the value and the units of the rate constant, and they came out to this answer. The units were cubic centimeter over molecules times seconds. So seconds being on the bottom. All right. So the question is, does this correspond to the units that would make sense with this mechanism? So notice we have a little bit of a difference in conversions here. One thing we can note is that it's pretty simple with Avogadro's number that we can convert molecules to moles, right? So we can say, okay, this is something that could be, it's a unit of amount, so moles is where we can convert it. What about this unit, cubic centimeters? It's a unit of what? Oops. Cubic centimeters, unit of I'm not doing it. Well, piece, but I'm not doing piece. I'm doing V, volume. Yeah, volume. Volume, thank you. So the units here are volume over moles. If we remember our formulas, we don't have a formula that's specifically volume is over moles, but what if we flip it? Moles over volume. What is that? Molarity, right? Molar. So K, if we converted it, would have units of inverse molar, inverse seconds. Going back to lecture 2, those were the units of a second order rate constant. So, in fact, this paper also uh, also concludes that the reaction has to be second order and actually has a rate law that we see here. Always good to do the dimensional analysis, always good to see that things match up with us. Oh, and I had a quick question in the chat about the elementary steps and Hess's law. And yeah, you can think of it the same way you did Hess's law in first semester, where you had a desired reaction. You wanted to see which combination of reactions would add up to that. We're doing the same thing with mechanisms. In this time, what we're saying is I have a series of steps, and the first thing I check is that do they add up according to Hess's law to make the answer, to make the overall balanced chemical equation? Trying it with another example, here is the reaction between iodine monochloride and hydrogen to make hydrogen chloride gas and iodine. So it's a different reaction. Reminder that we get the rate law of a reaction based off of experiment only. So R equals K times H2 times ICl is our experimental rate law. And notice that this rate law has nothing to do with the coefficients of this reaction. The reaction's coefficients have nothing to do with the rate law. The rate law must come from experiment. So we have an experiment. One thing that we can do is then try to postulate, okay, I have this rate law. What kind of mechanism would reflect this? What kind of explanation could I give why I see this kind of mechanism? So perhaps we have two options. Mechanism A is a one-step mechanism, and mechanism B is going to be a two-step mechanism. So let's focus on the one-step mechanism first. What it suggests is maybe two ICl molecules and an H2 molecule just all come together at the same time. So visually, three molecules bumping into each other all at once. And they rearrange their atoms, they rearrange their bonds, they pay the transition and they pay the activation energy to get to the transition state, and then you just make their products. Okay, that could be a possibility. So the first thing we check is, does the mechanism match the overall reaction? Well, in this case, obviously it does, because we're saying it's a one-step mechanism, so the step matches the reaction. The next thing we check is, does the elementary rate law for the rate determining step match the experiment rate law? So in general, the mechanism's rate law is the rate law of the slowest step, the rate determining step. When it's one step, there's only one step, so it has to be the slowest step. So in this case, what would be the rate law for mechanism A? The rate law, R equals K for that step, times the molecularity. How many molecules and what kind of molecules are colliding in this explanation for the reaction? Well, we have a hydrogen molecule, so it has to be based off of the molecularity of hydrogen, okay? And we have two ICLs. So, and we see it in this picture, not just one ICL is required, but a second one at the same time has to be required. So those have to count separately. So it'll have to be ICL times another ICL. So what does that make? This mechanism's rate law would come out to R equals K for that step times H2 times ICL makes ICL squared. So again, the rate law for a step in a mechanism is based off of the molecules colliding, and those are reactant molecules for that step. So two ICLs and an H2 comes out to H2 and ICL squared. Does this match, and does this match the experiment? Clearly not. Clearly not. There is no squared here. So this cannot be the explanation for how these molecules collide. So therefore we say, no, this cannot be two ICLs and an H2 come together and make products. In fact, three molecules colliding simultaneously has a really low probability of happening. You think about having a mole of molecules bouncing around all over the place. It's hard enough to get two of them to perfectly collide, but you want to have three of them collide at the same time. So three molecules colliding is really rare. Those are called termolecular collisions, and they don't happen very often. There are some rare happenings where that does happen, but in general, they don't really. Okay, so that is not our mechanism. What about mechanism B, which actually has two steps? The first step says, what if one hydrogen molecule and one ICL molecule come together and they make an HI and a HCl, and that happens very slowly for the reasons we described. Maybe the orientation is a problem, maybe the activation energy is a problem, but for whatever reason right now, it's the slow step. But once we get that step done, if an HI and an ICL get together, they'll make an HCl and an I2. Okay, so that is my explanation how the reaction happens. The first thing is, do these two steps make the overall reaction? Hess's law. Do these two steps. We have H2. We have two ICLs, ICL and ICL. Makes two ICLs. We have HI and HI on opposite sides. What do we do with those? Cross them out. Cancel them. Those go away. I see two HCl's and an I2. That comes out to my overall reaction. So this checks box 1 for a good mechanism. The next is, does the rate law of the mechanism match the experiment? So again, we're focusing on the steps. We're saying the first step is that tiny funnel that slows everybody down. That's the one that controls how fast we're going. So now let's focus on our rate determining step, slowest step. What is the molecularity? How many molecules need to collide? And what is the rate law for that? So the rate law, R equals K for that step times what? H2 and ICL. So that would be the rate law for mechanism B. Does that match the experiment? Yes, it does. So we would say mechanism B is a good explanation for how this reaction actually happens. And again, really, really nice, really powerful. What we're doing is we're taking real world measurements that we can make, right? Concentration, speed, can be things to measure in the lab. And we're connecting it to the microscopic picture, which is incredible. We say, because we know that the exponents of this rate law are 1 and 1, it cannot be a one-step mechanism. It has to be more complicated than that. And so that's what I mean by the fact that kinetics, the study of the speed of reactions, by doing those experiments, finding those orders, we can have a window into what the molecules are doing, which I personally think is super cool. Thumbs up if you think it's cool too. Oh, give me one. Oh, how do I? Okay. For the rate. Oh, one quick. Uh-oh. Why is my reaction? Uh-oh. Uh-oh. Oh no. Oh no. Can you guys still hear me?
Yes.
Oh, okay, because my computer froze. So I'm trying, oh, okay, it's kind of thinking about coming back. So while it's coming back, I'll keep talking. But Zoom is having an issue right now. So there was a question, how did you know that ICL had an exponent of 2? When it comes to the rate laws of elementary steps, the steps of a mechanism, you multiply by how many molecules there are. So I unfortunately can't, oh, actually, it's the same reaction as up here. 2 ICL plus H2 makes the products. So the rate law for that step is going to be the multiplication H2 times ICL times another ICL, because there are 2 of them. And that's where we simplify them, we get a squared, get ICL squared. So that's how we know that it had an exponent of 2, because the 2 counts how many ICLs there are, and the rate law Okay, I'm back now. Oh, okay, sorry about that. Uh, let me go ahead and go back to the slides. I have a pretty old computer that I'm in the process of replacing. Here, here. Oh boy. Okay, there we go. Another great question while I'm getting this up and running. Does whoops. There we go. Okay, there. Does the exponent signify molecularity rather than order? For the case of an elementary step, it's both. Both. Because the molecularity impacts how you form the rate law, and the exponent of the rate law is the order. So when it comes to a step in a mechanism, the order, the exponent from that step comes from both the molecularity and represents the order, like in the example we saw with the one-step mechanism. So it's important to emphasize this is our conversation with mechanisms, the explanation for reactions. When it comes to the experimental rate law, the one that we get for the reaction as a whole, the overall reaction, the order does not necessarily reflect the molecularity. So it's really important to emphasize the difference of that when it comes to the experimental rate law, the order is not reflective of the molecularity. But for a mechanism, the order does reflect the molecularity. Now, okay, so we've just done our example with the ICl plus H2 case. I wanted to follow up with just a little bit about vocabulary. So when it comes to what's going on analyzing a mechanism, a couple things. First off, the balanced chemical equation is called the overall reaction. Things found on the left-hand side of the overall reaction, those are always labeled the reactants, right? The things on the right-hand side are the products. When it comes to the mechanism, you'll have a list of steps to explain how the reactants become products. So each step is called an elementary step. The slowest step is called the rate determining step. And I will always give you this column you see here. So I'll say this step happens to be relatively slow, and this step happens to be relatively fast. There's no way to guess which is which. I mean, you can kind of develop an intuition, but I will give you, this is the slow step, this is the fast step, so that you can tell which is the rate determining step. One thing we noticed that in this mechanism, we crossed out HI. HI was made and then destroyed as a part of the mechanism. So it doesn't count as either being a reactant or a product. For that reason, we don't give it that label. We call it an intermediate. Intermediate literally means something in the middle, right? So an intermediate is found in the mechanism. It's part of the explanation, but it's canceled in the overall reaction. So the pattern to tell an intermediate from other things is that it gets made. So we see in step one, you make it. It's highlighted in red, and then it gets consumed. So that's a reactant now being used. It gets crossed out, so it's not a reactant or a product. It is an intermediate. One thing as we continue with more examples is that when it comes to rate laws, we said something very important in lecture 2. We said a rate law is an equation that relates how fast a reaction is to its reactants. So what that means is that a good mechanism should not have a rate law that includes intermediates, because an intermediate isn't something that we can add to the beaker that can affect the speed. It's part of the explanation that how to get from reactants to products. That includes, making it and then consuming it in some subsequent step. So the basics of mechanisms. Mechanisms explain how reactions happen using elementary steps. We should be focusing on the slowest step. The rate law of an elementary step comes from its molecularity. Good mechanisms must add to the overall reaction. Experimental rate laws match the rate determining steps rate law. And rate law should only involve reactants and never intermediates. And that comes into play in this analysis of a mechanism. So in this reaction, we have an NO molecule plus a bromine molecule making 2 NOBr. We went into the lab, we did experiments, and we found that the experimental rate law is R equals K times NO squared times Br2. So it's second order in NO and first order in Br2. And so that means it is third order overall. The accepted mechanism, so I'm already going to tell you this is a good mechanism, is a two-step mechanism. One thing about this mechanism that's a little bit different is we have a new notation. We have a double-sided arrow, an arrow that points both forward and backwards. So this is called a reversible reaction, which just means that something we haven't focused on before is that once you make the product, it is possible for the product to go back and turn into reactants. So that's a reversible reaction. We're going to see how this comes into play in analyzing this mechanism shortly. So the first thing we can do is say, does this add up to the overall reaction in order to be a good mechanism? And you have 2 NOs, we have a Br2. Okay, so that matches. The N2O2 will cancel. So what are those called again? Intermediates, so it's an intermediate, and makes the product, 2 products. So yeah, it adds up. What would be the rate law of this mechanism? By the rule of looking for the slowest step and looking at its molecularity, we set up R is equal to the rate constant for step number 2 times the concentration of N2O2 times the concentration of Br2. It does not match the experiment. And in addition, it has an intermediate in it. Intermediates are never in the final answer, so this is not a good mechanism. So at first glance, this is not a good mechanism, but I've already told you that this is the accepted mechanism. So there must be more to this picture. It comes down to the reversible first step. So again, a reversible step can go forward, make products, or go backwards, reverse, make reactants. And when we have a reversible reaction, we can write a rate law for both directions. So the rate law in the forward direction would be as we've already been doing it. So if we go from left to right, the rate law for any reversible step X, so step number X, the rate law would be R equals K for that step X times the molecularity. It's just one thing, A. What ought to go in reverse? If we go backwards, we have to read it backwards. So it'll be 2 B's get together and make an A again. So we would write it as the rate constant for the reverse of that step. And for that, we put a minus to go with opposite. So it's x going in reverse times the concentration of B times the concentration of B makes B squared. Because it's a B and a B and a B have to get together. So it's B squared. One thing that happens for reversible reactions, which we'll investigate in module 2 and beyond, is that reversible steps eventually, going back and forth all over the place, have to come into balance if you give them enough time. We call that dynamic equilibrium. Equilibrium being a word meaning balance. When that happens, the rate of the forward will equal the rate of the reverse reaction. That's what we mean by balance. Their rates going forward will eventually be equalized by the rate going reverse. So they'll still move back and forth, but they'll be perfectly balanced with each other. And when that happens, we're going to use this rule or this definition of balance to see why the previous slide's mechanism was correct. What we'll do is we'll say if our forward equals our reverse, then the red parts can be substituted to be equal to each other. So what would that look like? Now let's substitute. It will be this. It tells us kx times A has to equal k minus x times B squared. That's going to be the cheat that we use to make these, to make the previous example make sense. Okay. So here is just the example again. So this is the reaction, and we said it was a good mechanism, but it didn't work out correctly. So in red, you see what we got for the rate law of the mechanism, step 2's rate law, and it didn't make sense with the experiment. When it comes to a mechanism that has a fast step that is reversible, followed by a slow step, so that's the pattern, then we have another consideration. If this first step is truly fast, then the back and forth that's symbolized by this arrow, the back and forth will come into balance before the second step happens because it's really slow. So we know that during this process, while the reaction is happening, R1, the speed of step number 1, comes into balance with the speed of step number 2. So we have this. Using what we know about the last slide, if the speeds are equal to each other, then their rate laws are equal to each other, are equals. So what is the rate law of step number 1? And what is the rate law of step -1? It's the molecularity. So this is going to be K1 times NO times NO. So that's NO squared. And the reverse, if we read it backwards, an N2O2 goes back. So it'll be N2O2. So R minus 1 is equals K minus 1 N2O2. And again, let me know if there are any questions. So what we have are two true statements about our mechanism, right? These things are simultaneously both correct statements. One is the slow step controls the speed of the reaction. That's our red. And so therefore, this rate law should be what we experience in our observations. The second is this mechanism tells us that the first step will go back and forth until it gets into balance as part of the explanation of what's going on. So both the red and the blue are true statements. So if they're both true, I can kind of put them together as I see fit and still have a true statement. And so that's exactly what we're going to do. The thing is, we don't want this N2O2 intermediate here. It's not part of the overall rate law. So what we'll do is we'll see using the blue what it's equal to. So just moving things around, the concentration of N2O2 is equal to K1 times NO squared over K minus 1. I now have a true statement about the concentration of N2O2. It's equal to this stuff. And this stuff happens to be a reactant in the mechanism, which is better than having an intermediate in our answer. So what if I just substitute what N2O2 is equal to? That's exactly what I'll do. And so we see the red combined with the blue. There are a bunch of Ks. Ks are just constants. They're just numbers. So we can just absorb them into a single K, call it K overall, plug it in, what have you. So R is equal to K times NO squared times BR2. That matches the experimental rate law. So when it comes to mechanisms, the goal is to prove that a mechanism is an explanation, and it properly explains two things. It explains how the overall reaction works, so the steps have to add up to the overall reaction, and it has to explain what we see in experiments. So the mechanism's rate law must match the experimental rate law. Those are what we want to do with mechanisms. The second thing is there is one case where we have to do a little bit more work to prove that this is true, and that is with this pattern. There is a fast, reversible first step followed by slow rate determining step. Then we have to do a few more little mathematical maneuvers to prove that the rate laws match each other. So in most cases, it's just to prove it's correct, check that the steps make sense to the overall, and then find the rate law of the slowest step and make sure that it matches. The only time it gets a little trickier is with this pattern. There is a fast, reversible step followed by the slow rate determining step. And then we have to invoke reversible steps come into balance faster than the slow step. And that leads us to a second equation that helps us with the answer. Get to the answer, yeah. So that is our answer. This is the mechanism for that reaction that we were discussing. The reaction coordinate energy diagram that represents this reaction is shown on these axes. Remember the reaction coordinate, the progress, and the energy of reactants. So we have the energy of the reactants, the energy of the products. Remember that the difference between reactant on the left and product on the right, that's our enthalpy change, just like before. But you'll notice it's a little bit different than what we've seen in the beginning. There are two little bumps here. Why do you think that there are two bumps on this graph instead of the other example, there is only one? What do each one of these bumps represent? Anybody want to take a stab at that?
Is it each reactant? Like,
oh, sorry, go ahead.
no, I'm just kind of like trying to see like each reactant. Because now we have like two reactants and as opposed to one.
Two reactions?
Yeah,
two steps. Yeah, you're exactly right. Yeah, each one of these represents the energy to do each step. So we see two steps. Let me do the click. There we go. Yeah, the first bump represents the activation energy that I have to overcome to get through the first step. And the second bump represents taking the reactants of the second step and going over to get over the hill to the final product. So each one of these is an activation energy for each step, getting over their own transition state, that middle point, to go to the next part of the step. Yeah. One other question I'll ask is, do you think it makes sense, and why, that the sizes of these bumps look like this? This bump is kind of small, and this bump is kind of big. Is there anything about the mechanism that validates why we made the sizes like that? Is there anything the mechanism says?
Wait,
Is
can you
What
it
repeat the
about?
fast
question?
and
Can you repeat the
slow?
question?
Oh, so the question that I asked was, look at the difference in the shapes of these bumps, these activation barriers. And notice that the first step is kind of small and the second step is kind of big. And my question was, is there anything about the mechanism? Is there any information in the mechanism that validates the sizes of these barriers? And you are absolutely right, Lizette. It is the fast and the slow, right? We know from our discussion of the Arrhenius equation, that equation about those factors, that slow reactions tend to have something more challenging about their collisions. And one of the things that could be challenging about their collisions is having enough energy to start your reaction. And so that's what's happening here. The slow step implies the meaning of slow implies that there is more of a barrier to the reaction. And we see that in the graph. There is a larger effort that's needed to get the from beginning of step 2 to the end of step 2. And so that's something to keep in mind when making a graph like this, and I will ask you to make a drawing in shortly when we return. Make drawings like this, and acknowledging that if a step is challenging, it implies something like there must be a high activation energy versus a low activation energy would be a faster step. And then the other thing I'd like to reiterate is the top of the reaction. The reason why there is a barrier is because there is a point in the reaction where the molecules are rearranging in a way that's high energy, a way that they don't really like to rearrange. And we saw that with the hydrogen has to have a moment of half bonding to another H and another F, and they don't like that. So it's a high energy moment, and we call that a transition state. So the top, in terms of progress, again, X is progress. In terms of progress, that topmost point on the bump, tallest point at where we get to our activation energy, that's where we're reaching this unfavorable high energy state that we call the transition state. So this is the transition state for step number 1. It's when the NO and the NO have a hard time rearranging to get to their product. And then this top point called transition state 2 is when the N2O2 and the Br2, they're rearranging to make their product NOBr. And so this highest point is in terms of progress, is called our transition state. And the distance of energy that we're measuring is called the activation energy. Okay. Whoops. The final thing is there's one more aspect of mechanisms that can be involved that we haven't seen yet, and those are catalysts. A catalyst is a chemical substance involved in a reaction with the following properties. It facilitates the reaction. It increases the rate, makes it easier for the reactants to become products. However, it is not consumed by the chemical reaction. In other words, it could be consumed, but it's somehow remade in the mechanism. So overall, we get it back. And so that's what this kind of image is representing, that the catalyst helps the reactants become products, but it circles back and becomes remade. It does not influence the final concentrations. This is going to be important for module 2, that it makes things faster. It doesn't get used up in the process, but it doesn't influence the final concentrations. You will get the same amount of product, whether you use the catalyst or not. The catalyst doesn't have that power over the reaction. To give you an example of a reaction with the catalyst, let's take a look at this mechanism. This is the mechanism for, unfortunately, the depletion of the ozone layer by those pesky refrigerants that were being used prior to that being phased out. So chlorine atoms had an issue with ozone. So there's a two-step mechanism for ozone and what happens to it. So my question to you is, using Hess's law, what happens to ozone? What is the overall reaction? According to the definition of a catalyst, are there any catalysts? Remember that we look at number 2. It can be consumed in the mechanism, but it has to be remade at some point. Okay, is that happening here? And then are there any intermediates in the mechanisms? Remember, an intermediate is something that is only seen in the middle, only in the middle of the reaction. So take a look, take a stab. What is the overall reaction? What happens to ozone? What are the intermediates? What are the catalysts, if any? We're doing Hess's law here. So if you said the overall reaction is O3 plus O makes 2O2, I would agree with you. So ozone is depleted by this reaction when those pollutants come into contact. The catalyst is the chlorine atom. It helps, it's part of the process of what's going on, but we see that it gets used up in step 1, but then it's a product, it's remade in step 2. So that is our catalyst in this case. Are there any intermediates? That would be ClO is our intermediate. It is made in the reaction, but then it is used up in another step. So one thing to emphasize is that neither catalysts or intermediates are in the overall reaction. They both cancel. The difference is how they cancel. Catalysts cancel because they are a reactant first and a product second. Intermediates cancel because they are a product first and a reactant second. And so we see that's the case here. And so it follows this picture. The ozone and the oxygen atom come into to do a reaction. The chlorine helps by doing some help in the step, but like this circle suggests, eventually it gets remade. And that's a bad thing for the ozone layer, because that means a chlorine atom can then do it again and again and again and again until something else has to happen to eventually stop it. So one chlorine atom can do a lot of damage to ozone. And that's what we call a catalyst. something that helps the reaction go forward, in this case, that's a bad thing, is not consumed so that it can keep going, and it doesn't influence the final concentrations. So there are a couple types of catalysts. Homogeneous are catalysts that are of the same phase as the reactants. And so the previous example was chlorine is a homogeneous catalyst because it is a gas just like the reactants, oxygen atom and ozone. Or catalysts can also be heterogeneous, meaning different phase. An example would be adding hydrogen atoms to organic molecules can be facilitated by adding solid metal particles. And so the reason why it helps is because the organic molecules and hydrogen can land more easily on them, stick to them, and it makes it more easy for them to collide and do their reaction. But in any case, no matter the catalyst, one thing is true, it helps the reaction, and it can do this by in several ways. But overall, the way we describe it is it in some way lowers the activation energy by creating a new lower energy transition state through one or more of the following: creating intermediates with weakened bonds, better orienting molecules, or increasing the rate of successful collisions. So that's a lot of words. How can it be depicted on a graph? Say we have a mechanism. How many steps is this mechanism? So it's one step, right? One activation energy. This is a one-step mechanism. It has an activation energy here. If we add a catalyst, the way we can tell it apart is because it must in some way make the activation energy lower than it was before. In this case, adding the catalyst turned it into a different one-step mechanism that clearly has a lower activation energy than before. But it's not uncommon that the catalyst can cause a different mechanism, something with more steps, perhaps, like this one, which now is a two-step mechanism. But again, the change is that it has a lower activation energy than before. And if my activation energy gets lower, my reaction overall gets faster. So catalysts have to help the reaction by in some way lowering the activation energy. And one example is enzymes, biological catalysts. So proteins are these catalysts that catalyze one or more chemical reaction in living systems by acting on substrates, the reactant specific to that enzyme. And you may be familiar, if you've taken biology class, about the lock and key mechanism. So an enzyme, typically, the way it helps a chemical reaction is it's specifically built to have almost a landing zone for the molecules to get them close together. So we call that the lock and key model. And when those two molecules both, with their perfect fit, lock into the enzyme, they are now in a place where they may, one, have more collisions with each other because they're so close, and two, collide at the proper orientation because they've locked into the enzyme in a specific way that, hey, now it's perfect. And then they end up making their product. So enzymes are an example of catalysts. They lower the activation energy because they cause more successful collisions in the correct orientation. And in many examples of enzymes, they lower the energy necessary to react. So all of those wrap up into a biological reaction with a lower activation energy than without. And that's how enzymes help our bodies and help life happen. So hooray for enzymes. There's your example. That connects to biology. And so here we have it, our summary of module 1. Basically, we have finished module 1 by connecting our discussion of reaction kinetic speed to what is going on inside the reaction. We can connect all of our experimental data to the to the collisions of molecules and use those rate laws that we develop to determine what best explanation do we have for how the reactants become products. And those are called mechanisms. All right, so that concludes the lecture for today. Sorry about the typo, or not the typo, but the technical difficulties for that. At this point, I'll be happy to take questions. I see a question in the chat. So the question was, so obviously we can't do experiment 0 in person because it is not safe to return to campus yet. You know, tentatively, they're saying that we can return on Monday. So let's plan on meeting in person on Monday. One question is about lab partners for experiment 0. So that was going to be the first thing that we did for experiment 0 is pick lab partners. So normally I would offer that if you have a lab partner, then you can go ahead and collaborate on the report. I mean, that's how I did it before. So I guess what I'll say is if you have already had a discussion with someone in the class and they agreed to be your lab partner, then you can collaborate on experiment 0, and then we'll go from there and you can formally decide. Just when you submit, let me know that both of you agree to being lab partners for the rest of the winter. However, it is, and I've seen it done many times, doing experiments individually has positive results on everyone in terms of their understanding. So keep in mind, there's nothing wrong, and I've seen many a student do individual lab reports. It's very doable. Tomorrow is also Zoom because it is not safe to go to campus, and tomorrow is the start of module 2. So now you go to the next next module links, and it should be already open. If there's an issue with that, let me know, but I think it's already open. We are going to be talking about the next chapter, and that's what module 2 is, chapter 16, where we will in more detail discuss equilibrium. Tomorrow, yeah, and I'm describing, yeah, we are still going to do Zoom on Friday because winter goes fast. We really need to keep on the schedule, and that's what we'll be doing. When is the experiment 0 report due? That's a good question. So I'll tell you what. I know I moved the pre-lab because I don't want there to be what's going on right now being an issue with the submissions. I'll also make the report due Monday. And the reason why is because I do want to give you guys an opportunity to see me in person. And if you have any questions, you can ask them during class or during the breaks in person, because I think in person is a lot easier to answer the questions. So it'll give you a chance to have a day with me that if you want to ask questions before you submit, you can. So yeah, thank you for reminding me about the report due date. I'll move the report due date to Monday so that everybody has the opportunity if they want to ask questions with me. That being said, if you want to ask questions over the weekend, you can, but I do find that it's easier to answer questions in person. But please make an effort to work on it before, because there is certainly a time-consuming aspect to it, especially because it has Excel involved in the process. And when it comes to tomorrow, I also want to emphasize that tomorrow we do have a dry lab. I will be on Zoom during the lab period, and what I'll do is kind of like what we saw before. I'm going to give you an activity. I'm going to send it over Canvas this time, and I'll give and like before, we'll check it in person when we meet. And if you if you show me the completeness, I'll correct it. And by the end, if it's all correct, I'll give you your points. I should also say that the dry lab helps with one aspect of the experiment 0 report. So, so if you're going through the report and it's talking about making an Arrhenius plot, that's what the dry lab is for, to give us practice with that. So I will give you the explanation and the practice tomorrow morning for that. A question about quiz 2. Yeah, quiz 2 is only covering module 1. So because of the scheduling, it will be all of module 1. So when we see each other in person, we'll take that quiz. And that's not a big deal. I just like to break it up for the first one for students so that they can ease into the quizzes. But you know, from our discussions, our class, I fully believe, can handle it. As far as contacting me, I'll respond to anything, but I like so Canvas message versus email. I'll respond either way. I do like Canvas because it puts everything for our class all on that website instead of having to go to the web to email, then to Canvas, then back. But I'll respond either way. But I like Canvas. When will the dry lab be due? It'll be due when we see each other in person. So the earliest it'll be due will be Monday. And I'm pretty sure, I'm looking outside right now, pretty sure things will be good by Monday, I think. So yeah. Anything else before we head out? Okay, well, if there are other questions, feel free to hang out. Otherwise, I will stop this recording. I will send it out on Canvas message, and I will make those updates in an announcement that I mentioned right now here, so that we are all aware.